Welcome, ladies and gentlemen, to the video covering practice problems for combined gas law math problems. So there are several smaller gas laws that fit into the context of combined gas law. And remember that this means that pressure, temperature, and volume might be changing, but the amount of moles of gas is constant. So there are three relationships that build together to create the combined gas law. We have Boyle's law, which relates pressure and volume. We have Charles' law, which relates volume and temperature. And then we have Gay-Lussac's law, which relates pressure and temperature. And all of these will involve a set of gases where there's a change in one variable that affects a change in another. So there's a before and after to the conditions in the setup. And we're going to look for that in the problems we see. So first we'll annotate. So as I've labeled the conditions, anything that was related to initial conditions I called 1. So we have V1 of 30 liters and P1 of 103 kilopascals. And we want to find the volume, V2, of the helium when the balloon rises to an altitude where the pressure is only 25 kPa. That's my P2. So given that we have volume and pressure, this is going to be a Boyle's law problem. So at this point, I have three of the variables I need, and I simply have to solve for the unknown. So I'm going to plug in and figure out what I have so far. So at this point, I have V2 on the right multiplied times a factor, and I have math variables on the left for my pressure 1 and volume 1. So to get V2 all by itself, I'm going to divide both sides by 25 kilopascals. And my calculator says 123.6, but given my 25.0 kilopascals or 30.0 liters in my sig figs, I'm going to round to 124 liters. So let's double check our relationship. In Boyle's law, to maintain the constant, as pressure would go up, volume would go down. There's an inverse relationship. So our initial volume was low and our pressure was high. Pressure decreased, so volume should increase. Going from 30 to 124 makes sense. Next question. So here we see a reminder that the pressure is constant, and the only variables at play are volume and temperature, which means we're using Charles' law. So much like I did before, I'm going to plug in the variables I've identified from the problem. I have T1 and V1 conditions, and figure out my volume 2. Kind of nice that it's up on the top of this, so we're going to have a few options when we solve mathematically. Now, one additional piece we have to consider here is that because temperature is involved, we do have to care about our units. Here we are presented Celsius, and we can only do temperature calculations in Kelvin. So for each temperature that we're going to work with, we have to add 273 to convert from Celsius to Kelvin. Remember that Kelvin does not use the degrees sign. Now in this case, V2 is all by itself we need to get V2 all by itself. I can either cross multiply or multiply both sides by 331. That's my favorite because it seems like a simpler step. Make sure that you guys are not being lazy in your work. You cannot use parentheses and multiply an entire equation that way. It just isn't the way that it works. So once I do my math on the left of 331 times 4 divided by 297, we get 4.4579, etc. And rounding to my significant figures of 3, I get 4.46 liters. So here, instead of being an inverse relationship, it is direct. When we take a look here, the temperature went up, so the volume should go up, and mathematically our answer supports that. So Charles' law, we see following the pattern. Next question. So noticing here that there's no indication of anything about volume, we're looking at Gay-Lussac's law with pressure and temperature. Again, because we have temperature involved, we must convert to Kelvin from our Celsius, so we're going to do that for both values. So 928 plus 273, can't do that one that quick. We get 1201. So again, I'm going to multiply both sides times the 1201 to clear out that part. Again, cross multiplying will work as well because you're using a ratio. I just like to do it this way, but you will be fully supported if you do it the other way. And our answer with correct sig figs is 415 kilopascals. So here we saw a large increase in temperature, also a great increase in pressure, which makes sense with a direct relationship. Remember that as long as we're working with pressure, you can solve for whatever unit is in the unit of the original. The temperature is the only one at this point where we must convert to a different unit. We must be in Kelvin if we're doing temperature. Okay, so last problem. All right, so notice that we have volume, temperature, and pressure all at play in this problem, so we have to use the combined gas law. We are also introduced to STP with this problem. Remember, standard temperature pressure would be 1 atmosphere pressure and 273 degrees Kelvin. I'm sorry, 273 Kelvin. And if we look at kilopascals, 1 atmosphere equals 101.3 kilopascals. So I'm going to begin plugging in my values. So I am going to show cross multiply this time just for the sake of a different method, but multiplying and dividing the same thing on both sides will work. Then at this point, all we have to do is solve for our unknown. Applying significant figures to our answer from the calculator, we should get 39.5 liters. The trick for these problems is to really make sure you are labeling and annotating well, which is going to help you decide which gas law rules to apply. The other thing is knowing your proportions and understanding the relationships between the variables will help you predict what the number should be, so when you get your answer, you'll know if you did it right. Also, notice how much I'm emphasizing using the units in the work, and then canceling out helps us justify and make sure that the answer we get at the end makes sense in terms of what we're solving for. So the notes are all supported in the PDF document that's attached, but this was a way for you to see some of the problems annotated and worked out. Enjoy your time doing your gas law problems.